Dear students, let us continue our learning the course Data Structures and Applications. We are in the ninth session of the module 4. The topics covered under this session are binary search trees. The operations of the binary search trees involve definition of the binary search tree, inserting an element to the binary search tree, deleting an element to the binary search tree, traversing and searching the binary search tree. Myself, Dr. Suresha.d from the Department of Computer Science and Engineering of Canara Engineering College, Bantwal, Mangaluru. So earlier we learned binary trees. The key factor of the binary trees are the maximum we can have the 2 children over there. The binary trees either we can have the 0 children or we can have 1 children or we can have the 2 children. That is the maximum degree for any node in the binary tree was degree 2. But there were no rules on the arrangement of the elements in the binary trees. Elements can be inserted in any form. We can have the insertions can be done over there, or we can create the tree over there. The only restriction in the binary tree was the degree of a node. Maximum we can have a degree of 2. The binary search trees are an improvement over the binary trees, wherein they are also called as the ordered or the sorted binary trees. So there is an limitation or there is a regulation on the arrangement of element in the binary tree. Such a tree we call it as a binary search tree. So these are the particular type of container, that is data structures that store items, numbers, names, etc. in the memory, but they allow us for the faster lookup, the retrieval. Why we go for arranging the elements in an order is we need to have the faster lookup, faster addition and faster deletion of the items can be used, and they can be either we can go with the dynamic set of items or we can go for the lookup tables can be used over there using a key element if you want to search. Suppose let me take an example. If I have a element called 10 and this is my list, the list is, suppose if it is a 12, 18, 4, 10, 15. Now if I want to search for this 10 over there, assume, then I need to search the first element, the number of comparisons is 1, second element, the number of comparison is 2, third element, the number of comparison is 3, fourth element, the number of comparison is 4, fifth element, that is on the fourth element I am going to get my element. That is I made the 4 comparisons over here. So instead of that one, if I have the elements sorted. So now what happens, the elements are sorted means the elements will be in the order 4, 10, 12, 15, 18. So now in this one I want to search for the 10. So as with our binary search, what you learned earlier, the same concept, we search the element middle element. If it is below that one, then what we'll do, the element is present in the second half. Then we again make the middle element over here, the middle element among the 4 and the 5, 10, that is the 4. That is your first index. If not matched, then we'll go to the second one, that is the 10 over there. So how many comparisons we made? We made the 3 comparisons. Earlier we made 4 comparisons over there. That is, the efficiency will be improved. When we go with the sorted elements, and if we go for searching an element in a sorted list, then the efficiency will be improved over there. That is the advantage of having the sorted tree. That's representation, we call it as the binary search tree. They will improve the searching time. Even that insertion and deletions will be efficient. We will discuss this factor as we continue. If you go with the next, binary search trees keep their keys in sorted order so that lookup and other operations can use the principle of binary search. What is the principle of binary search? We start from the middle element. If our key element is less than the middle element, then we search the first half, or if the key element is higher than the middle element, then we search the second half. The same logic we will continue over here. That is, it is based on the principle of binary search. That is, when looking for a key in a tree or place to insert a new key, they traverse the tree from root to leaf, making comparison to keys stored in the nodes of the tree and deciding based on the comparison to continue searching in the left or the right tree. On average, this means that each comparison allows the operations to skip about half of the tree, so that each lookup, insertion or deletion takes time proportional to the logarithm of the number of items stored in the tree. This is much better than the linear time compared with the to find the elements of a key in the unsorted order, but slower than the corresponding operations on the hash table. Right? That is the advantage of having the binary search tree is the insertion, deletion, the as well as searching can be done in a more efficient way, that is in a logarithmic time when compared to the linear time. That is logarithmic, the complexity for your binary search tree will be your log n, but for the normal regular trees this will be n. Normal regular trees it will be n, but for your binary search tree the complexity will be the logarithmic of n, which is similar of the binary search what we have studied earlier. Next, how the elements will be inserted over there. The first key point is each node has exactly one key over there. Means no repetition is allowed. Only one copy will be present and the nodes of the tree, that is the keys in the tree, all are distinct. Second one, the keys in the left subtree are smaller than its root and the keys in the right subtree are larger than the root. Then the left and the right subtrees, they are also again the binary subtrees. Let me take some example over here. Suppose I have a list of elements, say 10, 8, 15, 22, 9. So now I want to create a tree for it. First we start with the root 10. So next 8. So when before inserting we check with the root, its root. 8 is less than the 10, so the smaller element will be inserted as a left child. So 8 will be the left child of the 10. Next element 15. 15 is higher than the 10, so it will be inserted as the right child of the 10. Next element is 22 compared with 10. 22 is higher than the 10. Go to its right child. Again 22 is higher than the 15. Go to its right child. Connect it as a right child. Next element 9. Now the 9 is less than the 10. Go to the left child. 8. 9 is higher than the 8. So connect it as a right child. Next element to be inserted. Let me take it as a 14. I want to, next element 14 I want to insert. So 14 is higher than the 10. Go to the right child. 14 is less than the 15. So connect it as a left child. That is the insertion, deletion as well as the traversing will be done in an efficient way. What is that rule over there? Simple rule. All the left child should be less than the root. Second one, all the right child should be higher than the root. The next point, each element will be distinct. The same rule you should continue for the left and the right subtrees. Whatever the rule we told, the first three rules, the same rule you have to continue for all the children over there. This is the main mechanism of the binary search tree. Next, the different operations on the binary search tree. There are mainly three basic operations. The first one is inserting the element to the binary search tree, deleting the element from the binary search tree, and searching for an element in the binary search tree, we call it as a lookup. First, searching. Searching a binary search tree for a specific key can be programmed recursively or iteratively over there. Let me take the binary search tree. Let the tree be in this format. Let me have the tree in this format as 10, 7, 9, 12, 11, 14 and the 13. Now I want to search for 13 over there. How the searching will be done? First 13 is compared with the 10. My key element to search is 13. 13 is compared with the 10. Yes, it is higher than 10. Go to its right side. 12. 12 is compared with the 13. Yes, 13 is higher than 12. Go to its right side. Next, 14 is compared with the 13 now. 14. 13 is lower than the 10. So go to its left side. So now here we have the elements. How many comparisons we made? 1, 2, 3 and the 4. This is the main logic behind the searching. Fine. So now how this will happen in our programming? Let us learn. So now we begin by examining the root node. What is the root node here? 10 and the 13. If the tree is null, then the keys we are searching for does not exist in the tree. Directly we say that the element is not present. If not, if the tree is not null, then we keep on moving till the key becomes equal to the root. How we will do? If the key equals to the root, then the search is successful and we will return that node. If not, if our key is less than the root, then we search our element in the left subtree. If the key is less than the root, then we search our element in the left subtree. Similarly, if the key is greater than the root, then we search in the right subtree. This process is repeated until a key is found or the remaining subtree is null. Till this point, this will be continued. If we find the element, we are going to give that element, and if we found that the subtree is null, then we say that the element is not present. If the searched key is not found before a null subtree, then key is not present in the tree. So this is the main logic behind the searching the binary search tree. How this happen in the programming? Let us look. Simple logic. So first, if root itself, here we are passing the root and the key. If the root itself is null, then we will return the null value. If your key searching it matches with the key element of the root, then we will return that node. That is, the element is present. Next case, if the element is not matching. Next case, if the key is less than your data in the root, then where we need to search? We will need to search in the left side. That is, now in place of your whole tree, you replace the root of left side and the key element. Or else, not equal, not less than. What is the next option? Next option is it should be higher than our root. Then where we need to search? We should search that one in the right child. That is, search root of right child for that key element. So this is the repetitive words, what we call the recursive function, what we have implemented. Instead of recursive function, if we want to go for the iterative one. So now this will be repeated by a loop. So we have to repeat till there is no null node we have. Next, if k is equal to your key element, then return that value. Or else, what is the tree value? Tree you should move to the left side. Tree will be equal. That is, if key is less than the node value of the root. That is, if key is less than the tree of data dot key, then tree equal to tree of left child. Means we search in the left half. If not equal, not less than. What is the next option? It should be higher than. Then where we need to search? Search in the right child. Now we completed this one. So now to come out of this one, either I should get this return statement or the tree value is null. If I get this return statement, means the element is present. If the element is not present, then the tree value will become and will return the null value over there. So null value indicates the element what you are searching is not present. Right? So this is the main logic behind the search operation. This can be implemented both in the recursive way as well as the iterative way. And both the functions are shown over here. Recursive and the iterative functions are shown. Next. The above example what we have discussed, they depend on the ordering of the tree. If the order relation is the only total pre-order, a reasonable extension of the functionality is also in case of equality search down to the leaves in a direction specifiable by the user. A binary search tree is equipped with such comparison over there. So that is, if you remember your pre-order traversal, the sequence you know that one. What is that one? First will be the root. Then next we will search for the left subtree. Then next we go with the right subtree. The same sequence we are following. If the element matches, then we match with the root. If the element is less than, then we'll move to the left child. If the element is higher than, then we'll move to the right child. Then we'll move to the right child. Fine. So now if we go with the complexity of this one, on an average, this tree will take up big of log n, where n is the number of nodes, where n is the number of nodes over there. So on the worst case, means if your searching element is not present, then at the maximum we can have big of n height will be the your cases. Fine. So this is regarding the complexity of the binary search tree search. Next, inserting an element to the binary search tree. How the element will be inserted? Let me take the tree as, first let me discuss the example which is present. So now I want to insert an element 35 over here. So this is my existing tree and I want to insert an element 35. 35 is compared with 30. Yes, what happens? 35 is higher than the 30. Where to connect? Connect to the right child. So now I will go to the right child. 35 is compared with the 40. 35 is less than 40. Yes, now no elements are there, so connect over here. This is the main logic behind the insertion. Fine. So we are not shifting anything, not replacing anything. We are just connecting them as a child. Let me take one more simple example. I have a elements as a 10, 5, 15, 8. Now I want to insert the element 9. Next element is 9. How to insert? 9 is less than the 10. Go to its left child. 5 and the 9. 9 is higher than the 5. Go to its right child now. If it is higher, then right. If it is lower, left. Next, 8 and the 9. Now 9 is higher than the 8. So connect it as a right child. We are least bothered about balancing the tree over here. We are not balancing anything. For inserting, quite simple logic. Suppose the next element, what I need to insert is a 14. So now 14 is compared with the 10. 14 is higher than the 10. Go to the right side. 14 is compared to the 15. 14 is less than the 15. So connect it as a left child. Connect it as a left child. Fine. The new nodes are introduced only as the leaf nodes. We are not replacing anything in the middle. The nodes are inserted as the leaf nodes over there. Along with that one more feature is why insertion is simple. If your key element, you know what you want to insert. If it is less than, then you need to go to the left subtree. If it is higher than, then you need to go to the right subtree over there. Right? That is, insertion begins as a search. Same logic would begin. If the key is not equal to the root, we search the left or the right subtree. How we search? If the key is less than the root, search in the left. If it is higher than the root, search in the right. Eventually, we will reach an external node and attach the new value pair as it's a left or the right child, depending on the node's key. In other words, we examine the root and recursively insert the new node to the left subtree if the key is less than the root, or the right subtree if the key is greater than the root. Normally, the equal to the root is not considered, but for the theoretical explanation, even that equality case will be taken for the right tree. For the theoretical case, for the practical implementation of the binary search trees, duplicate values we can't have. That is, the element should be unique. Let us go with the function for the insertion. First, the element will be, the tree will be the tree pointer node. The element I want to insert is k. Next, first will be the modified search. We are going to have the modified search. Then we will, how the modification will be done, let us look. Fine. If the temp equal to your content in the node, then the k is not in the tree. Next, we go for allotting the memory for it. Next, the key element we are going to attach. Data element we are going to attach. Then next, initially we take left child and the right child will be equal to null. Initially the left child and the right child will be equal to null. Next, if the node what we are going to insert, fine. So now we are going to insert it over here. How the insertion will be done? Insert as a child of the temp. So how that temp insertion will be done? K will be equal to, if k is less than the temp of data, then k is your left child or else k is your right child. Then return your pointer value, return the node value over there. Fine. So this will be the insertion procedure. This is the insertion procedure over here. That is, if your key value is less than the root, go with the left. If the key value is right than the root, higher than the root, go with the right value over there. Next. So this part, that is a rebuild, uses the log n space. On an average case, it is the big of n in the worst case. In the earlier versions, the operation requires a time proportional to the height of the tree. In the worst case, that is a big of log n time in the average case over all the trees, where big of n is the worst cases over there. So another way to explain insertion is that in order to insert a new node in a tree, its key is first compared with that of the root. If the key is less than the root, then compare with the key's right child. Key, that is key to the root's left child. If the key is greater, then it is compared with the root's right child over there. This process continues until a new node is compared with a leaf node, and then it is added as this node's right or the left, depending on the key value. If the key value is less than the leaf key, then it is inserted as a left child, otherwise it is inserted as a right child over there. There are in many other ways are also there for inserting, but the nodes are inserted as the leaves over there. Then the deletion. So when we go for deleting any node, so let me take up one example. So let it be 8, 6, 10, 14 and the 9. So now I want to, there are two options are there. Either I will delete the leaf node or I will delete the intermediate node. I will delete the leaf node and the intermediate node. So now if I make the in-order traversal for this one, the sequence will be first is 6, 8, 9, 10 and the 11. Right? Now if I want to delete, sorry it is 14. It is 14. Now I want to delete this 9 or the 14. This can be deleted directly. No problem. I can delete them directly over there. No issues over there. That is, the deleting a node with no children is simply you have to remove that node. But if I want to delete the one which will have a child, right? So now for that reason, I want to delete this 10. Now I have the two options left out. First, I will take up the left child and I will replace over here. First option. Then its left child is taken and its left child is taken like that. That is your in order predecessor. Or the one more option is I will take the in order successor. I will take the 14, then I will continue over there. These are the two options which are there in front of us. That is deleting a node with one children. If it is a single children, no issues. Just that children I can connect it over here. But when I need to delete a node with two children, then call the node to be deleted as n. Call the node to be deleted as n. Do not delete n. Instead, you have to choose its in-order successor or its in-order predecessor. Copy that value to the n. Then recursively keep on deleting on R until reach one of the first two cases. Then that is the leaf value will be copied to its parent. Leaf value is copied to your parent. Means in place of 10, 9 will be copied. Fine. Then next cases. Then when you reach your leaf, then you discard that leaf. Then when you reach the leaf, then you discard the leaf. Right? So this is how we perform the deletion. For the deletion, three operations. That is a node with no children, directly delete. Node with one children, that child value you put to your parent value. Deleting with the two children, you take the in-order predecessor or the successor. If you take predecessor, every time you have to take the predecessor. That value you need to copy to root. Value you need to copy to root till you go to the child. So once you go to that child you discard it. Now let us look at the example which is present over here. So now in this case we have taken the in order successor. If the in order sequence will be like this, your elements are this node I want to delete. Now this is your in order predecessor 2. That will be no successor, so this will be shifted over here. Fine. So this is how the deletion is performed in the binary search trees. So in this session, we learned the basic concepts of binary search trees. The binary search trees are the ordered binary trees in which the ordering is done as the root, the left child will be less than the root and the right child will be higher than the root. And this will be continued for the subtrees also over there. Then next we learned on searching the binary search tree is most efficient and it takes big of log n time, logarithmic time it will take. Then next we learned to insert the elements to the binary search tree. Then next we learned deleting the elements from the binary search tree wherein we have the three options, that is to delete a node with no children or delete the node with one child, then delete the node with the two childs. The references for this video are from the textbook Ellis Horowitz and Sartaj Sahni, Fundamentals of Data Structures in C, 2nd edition, University Press 2014. And Data Structure Sham Outline Series from Schumer Lippus, revised 1st edition, Tata Macro Hill 2014. Thank you.